Transverse waves. Physical sciences grade 10. What is the first thing that comes to mind when somebody says the word wave? Do you think about surfing the waves in Cape Town? Well, me too. Most of us have a basic sense of what waves are. We interact with waves all the times in our daily lives. Waves can be divided into two groups: transverse waves and longitudinal waves. In this lesson, we will learn about transverse waves. At the end of this lesson, you will be able to define a transverse wave. You will also be able to define and identify the amplitude, wavelength, crest and a trough of a transverse wave. And lastly, you will be able to identify points on a transverse waves that are said to be in phase or out of phase. To start our discussion, we must first try to answer a question. What on earth is a transverse wave? And to answer that question, we must revise the definition of a transverse pulse, which we defined on the lesson about transverse pulses. If you have not already watched that video, please watch it before this one. If we have a single disturbance moving through a medium, we refer to that disturbance as a pulse, as demonstrated on your screen. The medium is represented by the black dots. The black dots are the particles of the medium. At first, the particles are in equilibrium, meaning they are undisturbed. Then a pulse moves through our medium from left to right. However, the particles or the black dots move up and down. The motion of the pulse is in the horizontal direction, and the motion of the particles, the black dots, is in the vertical direction. The angle between the two directions is 90 degrees. This type of pulse, where the direction of motion of the pulse and the direction of motion of the particles of the medium are at 90 degrees with each other, is called a transverse pulse. But what if we did not just have a single disturbance, but a continuous disturbance that consists of several pulses, as demonstrated on your screen? What do we call that? You guessed it, we call it a wave. You see now why we had to first learn about pulses. Think of waves like train of pulses, like a train of pulses. Like with a transverse pulse, a transverse wave is a wave where the movement of the particles of the medium is 90 degrees to the direction of motion of the wave. The particles move or change direction in the vertical direction, that is up and down, and the wave moves from left to right. Let's then define a wave and a transverse wave more scientifically. A wave is a periodic continuous disturbance that consists of a train of pulses. A transverse wave is a type of wave where the motion of the particles of the medium is perpendicular at a right angle to the direction of motion of the wave. This is a transverse wave. We can draw a horizontal line here in the middle, and we refer to that position as position of rest or equilibrium. This is the position of no disturbance. If the red dotted line represents the equilibrium, we can all agree that the following points A, B, and C are the highest points on this wave. These highest points have a name. Can you guess what they are called? They are referred to as the crests of a transverse wave. The lowest points, D, E, and F, also have a name. Can you guess what they are called? They are referred to as the troughs of a transverse wave. Let's then define the crest and the trough of a transverse wave more scientifically. A crest is a point on the wave where the displacement of the medium is at a maximum. On the other hand, a trough is a point on a wave where the displacement of the medium is at a minimum. Keywords there: maximum for the crest and minimum for the trough. Let's take another look at our transverse wave. We can all agree that for this transverse wave, the distance from equilibrium to the crest of a wave and the distance from the equilibrium to a trough of a wave are equal. Those distances are referred to as the amplitude of a transverse wave. The amplitude simply refers to the distance from equilibrium to the crest or the distance from equilibrium to the trough. Let's then provide a more scientific definition of the amplitude. The amplitude of a transverse wave is the maximum disturbance or displacement of the medium from the equilibrium or rest position. The distance from one crest to an adjacent crest, for example, from A to B, is equal to the distance from one trough to an adjacent trough, for example, from D to E. This distance is known as a wavelength of a transverse wave. The symbol for the wavelength is the Greek letter lambda, shown in the brackets. This means that point B is one wavelength away from point A, and point E is also one wavelength away from point D. We can then define the wavelength of a transverse wave as the distance between any two adjacent crests or any two adjacent troughs. By adjacent, the term adjacent just simply means neighbor in this instance. We have now added more points on this transverse wave, points A to J. The distance between point C and H is the wavelength of this wave. We've already established that. This is the distance lambda between two adjacent crests, C and H. However, if you look carefully, you will also note that the distance between A and F, A to F, is equal to the distance between C to H, meaning that that distance is also a wavelength lambda. In the same way, the distance between B to G is equal to the distance between C and H, meaning it is also equal to the distance from A to F. In fact, this distance is also a wavelength lambda. In fact, if you look carefully, all the points on this table are one wavelength or lambda apart. A to F, B to G, C to H, D to I, E to J. How then do we define the wavelength of a wave using this new information? The wavelength of a wave is not only the distance between two adjacent crests or troughs, it is also the distance between 2 points that we say are in phase. But what does it mean when I say that 2 points are in phase? 2 points are said to be in phase if they are separated by a natural number multiple of wavelengths. I will explain what that means shortly. Let's say, for example, that points A and B are separated. Let's say, for instance, that point A and B are separated by one wavelength, lambda. We then say that point A and B are in phase. Point B and C are also in phase because they are separated by one wavelength. The same way points C and D are also in phase as they are separated by one wavelength. Point D and E are also in phase as they are separated by one wavelength. But we can also say that point A and C are in phase because they are separated by two wavelengths, 2 times lambda. Point A and D are also in phase because they are separated by 3 wavelengths, 3 times lambda. Point A and E are also in phase because they are separated by 4 wavelengths, 4 times lambda. 2 points are in phase if they are separated by a natural number multiple of wavelengths. For example, 1 times wavelength, 2 times wavelength, 3 times wavelength, 4 times wavelength, 5 times wavelength, 6 times wavelength, and on and on and on. Remember, natural numbers are numbers from 1, 2, 3, 4, 5, 6, 7, 8, and on and on and on. Therefore, we can now define the wavelength as the distance between any 2 points, any 2 adjacent points which are in phase. That is, if the distance between the 2 adjacent points on a transverse wave is a natural number multiple of wavelengths. Before we finish this lesson, it is important to mention that in the same way we have points that are in phase, we can also have points that are said to be out of phase. Points that are out of phase are not points that are not in phase. Those that are not separated by a complete or a natural number multiple of wavelengths are said to be out of phase. For example, point A to E are not separated by a natural number multiple of wavelength, so they are not in phase. That is, they are out of phase with each other. Point B to D are not separated by a natural number multiple of wavelength, so they are not in phase with each other. There are many other points on these transverse waves that are out of phase with each other, and you can determine them for yourself as an exercise. We have come to the end of this lesson. At this point, you should have an idea of what a transverse wave is and which point on a transverse wave is a crest or a trough. You also have an idea on how to identify and define the amplitude and wavelength of a transverse wave. Lastly, you can also identify points that are in phase or out of phase with each other on a drawing of a transverse wave. On the next video, we will discuss the frequency and period of a transverse wave.